So why are we decided to use air-based material as reinforcement in air-based material? So they say, according to the World Bank report in 2020, we realized that there's a myth of urban houses in Cameroon, more than 1 million in 2010 and more than 1.5 million in 2015. Also, according to the report of the United Nations in 2019, they say the estimation of the urbanization in Cameroon can reach 70% in 2015. That is why the Minister of Urbanization has started a project, who can be seen in the left figure, to build houses for the local population in the main town of Douala and Yaoundé. To achieve that, we have to use the 17th Sustainable Development Goal initiated by the United Nations in September 2015, who targeting to make to access the adequate, safer, and affordable house by the population by 2013. It also by the support developing country through financial and technical assistance to achieve sustainable and resilient building housing using local material. And for that, we have to take in consideration the climate change and the impact of the environment. So to achieve that, we have to design alternative material who can be help us to reduce the cost and also the sustainable of the materialness. So for that, we have to understand and also to design and improve the property of the air-based material. It has been shown in the literature that by using cement, lime, and some alkali activator agent, we can significantly improve the compressive strength and also the durability of our air-based material. Although that by using those chemical agents, we still have a weak tensile strength and also a crack resistance, who can be shown in the figure 1, 2, and 3, who is showing the crack propagation due to the loading, and 2 show the crack propagation due to crack shrinkage on the early age of the building. On the figure 3 show the degradation of the wall due to the weather agent. So for that, many researchers are using fiber as a reinforcement in air-based material to overcome those challenges. But there's a limited work in the literature who present the use of cellulose fiber as a reinforcement in the air-based material. Yes. So to understand this, we use the concept of material science paradigm to improve the performance and the durability of the air-based material by using matrix with air-based material. We have stabilized by cement. We also studied the particle size distribution and the water banding ratio and the rheology characteristics of the phase to understand the workability of our air-based matrix. We plan to use cellulose fiber to as a reinforcement. We have to understand the morphological, physical, and chemical property. Who help us to understand the reinforcement efficiency of the fiber that we are using. So for that now, we have to use a process, with extrusion process, will help us to have a good dispersion and also an orientation of the fiber in the matrix. We have to understand also the curing condition, who can have an impact in the hydration and also the hydration process of our matrix. So those 3 components will help us to improve the performance of our material due to the crack bridging and also the interface between fiber and matrix. By understanding this interaction between structural property and processing, we can achieve our material a sustainable and robust building material. So what is the main objective of this study is to use non-wood fiber and recycled waste fiber in order to promote the resource conservation and also the circular economy. For that now, we have to select the fibers from select the fiber. After, we have to optimize the performance of the matrix by using a stabilizer. In the end, we have to design our building material using matrix and fibers. So the project will complete to the production and characterization of pulp and nanofibrillated cellulose from selected plant and tropical plant. Waste recycle. To start that, what is the previous work who has been done? We have Ricasono, who studied cassava bagasse nanofibrillated cellulose, and realized that by producing nanofibrillated cellulose from cassava bagasse, we can significantly improve the crystallinity index and also improve the tensile strength of the composite by using that nanofibrillated cellulose as a reinforcement. Later, I studied bamboo fiber organosulfur. Realize that by varying the time and the temperature in the reactor, we can have at 2 hours and 190 degrees a pulp with significant high aspect ratio and also the good mechanical and morphological property. Later, Cohen studied the nanofibrillated cellulose from cellulose pulp fiber and realized that by 10 cycles nanofibrillated by using Musuka grinder, you can have a cellulose nanomaterial with greater moduli of elasticity and the diameter. Later in 2020, Supian et al. Studied empty football and realized that by using nanofibrillated cellulose to produce, by producing nanofibrillated cellulose from empty football, it can help us to increase the value of the end product because an empty football represents around 24% of the total oil bagasse. There it can improve also the aspect ratio, the component efficiency of our building, our material. Okay, what is the unsolved issue? The unsolved issue now is to use the tropical biomass like the raffia and also umbrella as a raw material for pulp and nanofibrillated cellulose. And also a carton pulp, which correspond to 17% of the to promote resource conservation and the circular economy. I don't know how to use. Yes. So now, what is the raw material that we are using? We are using raffia fibers. That is raffia tree, that is a raffia fiber who has been extracted. This cassava bagasse, the cassava, from the cassava we can have our cassava chip. The bagasse is usually used in Cameroon as a food for the animal. We have also casmango, who is umbrella food, who usually degrade after 3 days. So we can have now the bagasse we will use for this study. We have a Bambusa vulgarici, who is a type of bamboo, who is more common in Africa in tropical region. We have there also the bamboo boss. So what is the cellulose fiber? The cellulose fiber is just the production of the partial removal of the amorphous component of the vegetal fiber, which is lignin and hemicellulose. By removing that, we need a chemical agent, we have temperature and pressure, who help us to dissociate the cellulose from lignin to hemicellulose. Now the cellulose who will be obtained, which is in microsite, have to go through the Musuka grinder for nanofibrillation. If we have a shear stress that we have to apply to our fiber by using many cycles of nanofibrillation, we can have our nanofiber who will have a high aspect ratio, high specific area, high stiffness, and also a good reinforcement efficiency compared to the whole fiber. So what is the experimental method? We are using a cellulose pulp battery method, using soda pulping, using organosul pulping, by using ethanol. A recycle process, we use only water for the recycle process. Then we use bleaching process, will help us to have to reduce the other residue of lignin by using sodium chloride and glacial acetic acid. Now the mechanical pulping, we are using the mechanical nanofibrillation, we're using Musuka grinder at 10 cycle nanofibrillation. And now the obtaining cellulose fiber nanofibrillator has been characterized from mechanical, from chemical, physical, and morphological. It can be seen in the left that from the raffia fiber with the diameter of 1,231 micrometer, we can have by using organosul pulping the fiber with the diameter of around 31.1 micrometer. By using nanofibrillated cellulose, nanofibrillated pulp process, we can have a nanofiber with a diameter of around 1,110 nanometer. So by starting the process, we have to know the chemical composition of our raw material that we are using to predict, to choose which type of pulping process we have to do. So by using raffia, we realize that raffia has a high amount of cellulose, a low amount of lignin, which shows that it can easily be pulping by using just soda pulping. Umbrella fiber used to have a high amount of cellulose, lignin, and a low amount of cellulose, which shows that it will be difficult to produce cellulose pulp by using this raw material. Cassava bagasse, we show that it has a low amount of lignin, also low amount of cellulose, which show that by using this, the yield of production can be very low for economic purpose. So now we study the impact of the pulping process on the response, on the pulping process and on the type of fiber by using raffia fiber and cassava fiber. We realize that by using soda pulping and organosul pulping, this organosul pulping giving fiber with low yield of production compared to soda. But by doing characterization, we realize that there was really a significant removing of the amorphous part by using organosulfate compared to soda pulping. Now we study now the effect of the tip of pulping on the type of fiber by using raffia, cassava, bamboo, and recycled fiber. We realize that by using bamboo and recycled fiber, we have a high amount of yield of production, which shows that this really we have a significant improvement of the pulping by using this, so we can have a good economical impact by using those type of material. So also we study the X-ray diffraction from the raw material to cellulose pulp to the nanofibrillated cellulose. We realize that by applying pulping process on nanofibrillated, there is significant improvement of the crystallinity index, which showing that they are really removal of the amorphous part in our air-based our cellulose material. We also study the functional group by using FCI, and we realize that they are from the raw material to the pulp and the bleaching vapor. There's a removal of the amorphous peak, like in the peak of 900 who responded to the hemicellulose, and the peak of 1,242 and 1,512 who responded to lignin and lignin. Also, by the figure on the right, you can see that from the pulp to the nanofiber, there is significant reduction of the site, which shows that the efficiency of the process. What is the practical implication of this result? We show that by using umbrella fiber, we cannot achieve a pulp or nanofibrillated by using umbrella fiber due to the high amount of lignin and ash content. Also, there is feasibility to use raffia and cassava for nanofibrillated pulping, but economically it doesn't have a good implication due to the low amount of yield of production. The satisfactory result of the aspect ratio, crystallinity index, and also the yield of production by using bamboo and recycled fiber, which can be used as material for the reinforcement, which can be seen in the figure there. So this work has been published in the Journal of British Natural Fiber under Taylor and Francis. So the project 2 consists of the effect of cellulose pulp fiber in the physical, mechanical, and thermal performance of air-based material. So now, what is the preview work has been done by using air-based material? We have Denshiku et al. Who studied cellulose, recycled cellulose fiber in cement material, and realized that by introducing cellulose fiber, there are revision of the compressive strength and the improvement of the thermal insulation on the cement mortar. They also Koye et al. Studied bambusa toloe pulp in cement mortar, and realized that by using 6 or 8% of this cellulose fiber in the cement mortar, they are increasing of the modular rupture. But by using 10 or 12%, they are significantly development of the tenacity, which is showing the strength hardening behavior and continue increasing of the stress at the first crack. So, Ospodarova use waste paper recycled in the cement mortar, and realize that by introducing that cellulose fiber in the cement, they are reducing the density and the thermal conductivity of our cement mortar. Later, Ojo et al. Studied scissor, polymer, and eucalyptus, polypropylene and eucalyptus pulp, and realize that by using 0.5 to 2% of the cellulose fiber, there is no significantly improvement of the type of the gritty failure in the material, and suggests to use more than 2% of cellulose pulp to have a significant improvement of the reinforcement efficiency. Later in 2020, Munoz et al. Studied paper and pulp residual fiber in the air-based and the adult break, and realized that by 12% of that adult break, that cellulose fiber can significantly improve the compressive strength and reduce the thermal conductivity. So, what is the unsolved issue? Can we use that cellulose fiber to inhibit car propagation for plastic shrinkage and flexural loading? Also, can we use the municipal the carton board, which corresponds to 15 or 25% of the price or the cost of the virgin fiber as a reinforcement in the air-based material? The response of those questions will be of the objective for this project. So why are we using cellulose fiber in this study? Cellulose fiber, because it has a micro size, it will help us to bridge the car. You will have a significant bridging in the micro scale. By bridging that, it will help us to inhibit the car propagation in the pore, in the micro micro scale. Also, you increase the tensile strength and also the toughness of our material. So why are we using extrusion process? It has been shown in the literature that extrusion process on the air-based reinforcing short fiber can help us to have improve the distribution of the fiber in the matrix. It also align the fiber in the direction perpendicular to the applied stress in the flexural strength. Now, before starting the study, we decided to characterize our own material, which is soil material, which is soil and bamboo. We did site distribution analysis, we did mineral composition, chemical composition, activity limit. Also, the bamboo and recycled fiber, we studied the morphology and the density. Okay, and now before starting the thesis, he was able to determine what is the maximum stabilization, the optimal stabilization can be helped to improve mechanical and physical property. We vary the statement from 5 to 10%, and also we vary the curing condition with 24 and 60 degrees. Producing cylindrical sample, apply compressive strength and water absorption, porosity. We realize that by using 10% of the fiber in the material at a temperature of 60 degrees and the relative humidity of 10%, we have a significantly high mechanical property, a low water absorption and porosity. Later, the composite has been used now. We decided to use 10% of cellulose or cement as our reference material. Now we vary the proportion of the cellulose fiber from the recycled fiber and the virgin fiber is 5 to 10%, and now we produce the composite, prismatic composite and physical mechanical conductivity analysis. What is the result of the physical property? By studying what density apparent volume, we realize that more than producing the fiber in the matrix, they are increasing on the water absorption and porosity, metal they are reduction of the density. So this is due to the fact that the fibers have a low density, also have a high absorption capacity of the water. So that is why more we are increasing the water absorption. Also by studying the virgin fiber and recycled fiber, we realize that the recycled fiber were giving a low water absorption, a low porosity, and a high density compared to virgin fiber. So by studying the density of the individual fiber, we realize that recycled fiber has a high density compared to virgin fiber. Also, this can be due to the fact that by applying the recycling process, it behaves like a treatment who can have an impact on the modification of the water absorption and also the dimensional stabilization of our recycled fiber. Also, we study the dry sinking, moisture loss, and resident humidity of the fiber. We realize that the more we are introducing the fiber in the matrix, we are increasing the dry shrinkage, we are increasing the moisture loss, and we increase also the percentage of humidity. This is due to the fact that during the mixture of our fiber with the matrix, the fiber with a high capacity of absorption, they absorb water, and now when it's dry, when absorb water is swell, and now when it's dry, it came back to the normal position, normal dimension, and now it releases the pulse between fiber and matrix. That pore will be used as a water reservoir to absorb moisture. That's why we are increasing on that moisture during the dry process. Also, we study the mechanical calculation by using four-point bending test on the composite in dry condition and the wet condition. We realize that from the wet condition and dry testing condition, the composite reinforcing the fiber they were improving on the mechanical property by reinforcing fiber. And also, there was a transition from brittle to pseudo-ductile material by using fibers. Also, by comparing cellulose, virgin fiber and recycled fiber, we realized that recycled fiber were having a high reinforcement efficiency compared to virgin fiber. That is consistent with the result that has been shown in the physical property with the dimensional stabilization of our recycled fiber. They have a good bonding between fiber and matrix compared to the recycled fiber. That is why they are more improving by using recycled. Also, by studying the crack tip, we realize that the predominant model of crack tip bridging. So the fiber will behave as a crack arrestor during the crack propagation of our material. So also we study the thermal conductivity of our base material. We realize that more we are introducing the fiber, we are reduction of our thermal conductivity. Due to the fact that the fiber with a low density will help to reduce the thermal conductivity of our material. Also, we study the pH evaluation because the cellulose fiber can degrade in the high pH medium. So we realize that from the 1 day to 24 day, they say the reduction of the pH, but after 28 days, the pH is still high than 11, which shows that the fiber can be degraded with the time in the air-based matrix. So what is the implication of this study? This study shows that we can use cellulose fiber for recycle and plant fiber as a reinforcement in air-based material to modify the breathing the mode of failure of our material from breathing to solidity material. Also, we can use it to improve the comfort thermal in the block producing with this material. Also, the fiber have a negative effect that it absorb more water. It also increases the dry shrinkage. Although that value of the dry shrinkage is significantly low compared to the maximum value required, which is around 8%. So now this is the paper we have been published from the second project in Journal of Engineering. So performance and durability of cellulose fiber reinforcing air-based material. So what is the previous work we have been done? We have done so I will study coconut, palm, and cassava and bagasse in the soil material, and realize that by introducing those agricultural waste in the air-based material, we can improve the physical, mechanical, and durability. And also, Mustafa has studied straw fiber in lateral soil. I realized that by using 20% of the straw fiber in the air-based material, we can increase the flexural strength and the fracture toughness of our material. Later on, Kola Wole has studied the bamboo fiber reinforcing air-based soil material. I realized that by using 25% of those bamboo fiber, we can increase the fracture toughness and the flexural strength, and the fiber will behave as a crack arrestor in the material. Later on, OJ studied scissor and polypropylene fiber in alkali activated clay soil, and realized that those fibers were helping to improve the strength and the fracture toughness, and the predominant mode of rupture here was crack bridging. So what is the unsolved issue? Can cellulose fiber can modify the fracture toughness of the air-based material? Also, can cellulose fiber can improve also the durability again wetting and dry cycle of the air-based matrix? The response of this question will be the objective for this project. So this project, we use the same formulation what has been done for the project 2, but the difference that now that the fibers, the composite has the machinery at the dimension of 80 over 20 over 15, and now all the surface has been polished to see how the crack is moving. And we apply a 3-point bending test for flexural strength, and also 3-point bending test with displacement with single X-notch B to study the fracture toughness of our material under MTS equipment. So now, what is we study also the dimensional stabilization of our air-based material. We saw previously that by introducing cellulose fiber in the air-based material, they were increasing of the dry shrinkage. So we, after one test of the dry shrinkage, we decided to soak the fiber in the matrix in the water for 24 hours. They apply again the test of determination of the dry shrinkage. We realized that there was significantly decreasing of the dry shrinkage of the fiber or the composite after one wetting and dry cycle. And we did the third time, we realized that it was almost constant. The result is consistent to the moisture loss and also the percentage of humidity. This can be due to the fact that by applying one wetting and dry shrinkage, we already have a void between fibers and matrix. So by applying that shrinkage, you can have a precipitation of the fallen cement iteration, who can help now to produce a gel of iteration gel, who can help to densify the interface between fiber and matrix and will improve the adhesion between fiber and matrix. Also, We study the surface of the fiber, the unreinforcing and reinforcing fiber. We realize that there was presence of the crack on the surface of the unreinforcing fiber, which is showing that during the shrinkage there are some crack propagation, but the fiber were helping to reduce the crack propagation. So we study also the mechanical performance under three-point bending system. We realize that, and also the fracture toughness. We realize that by introducing the fiber in the air-based material, they are increasing on the modular rupture, increasing on the specific energy fracture toughness, but they are reducing on the elastic of modules. We're showing that by introducing fiber, we can our material, who was pure breathing material, can transit from breathing to ducting material. The fibers are significantly improved the crack propagation of our material, who can be shown in the fracture toughness. Yeah. In the fracture toughness. Also, by studying the crack tip, we realized that the mode of rupture was crack bridging mechanism was present in the crack tip region. Also, we went to the microstructure to evaluate what can be to understand more the mechanical and physical behavior. We realize that for the composite without fibers, we have less pore, which is consistent to the high density that we got in the physical characterization. And also by reinforcing fibers, we recycle fiber and the virgin fiber. There is a more adhesion between fiber and matrix from recycled fiber compared to virgin fiber. This can be due to the fact that the fiber has the recycled fiber can be applied as a treatment for dimensional stabilization of our fibers. So we study also the durability, again wetting and dry, by using ASTM standard D559. We realize that by using 12 cycles of wetting and dry treatment and applying by washing the surface of the material, we realize that the fiber was significantly reduced. After 7.5% of the recycled fiber, there's an increasing of the percentage of where we show that after that 7.5, the fiber they can have a cluster of fibers who can reduce the adhesion between fiber and matrix. What is the implication of the result? Say that we recommend to use one cycle of wetting and drying of this treatment of this air-based material reinforcing with cellular fiber to improve the water absorption and the dry shrinkage, if we want to use this as a building material. Also, we recommend the cellulose fiber also can help to improve the mechanical property of our air-based material. Also, we can have a crack bridging who can appear, who can help to transfer from brittle to ductile material. Also, it improve also the resistance to the durability, again, wetting and dry. Also, what is the conclusion of this work? That umbrella plant is not recommended to be used as a raw material for pumping due to the fact that they have a high amount of lignin, so it can be used as a feed for the animal. Also, due to the high value of the aspect ratio, production yield and crystallinity index, we recommend bamboo and recycled fiber as a raw material to produce cellular fiber as a reinforcement in the air-based material for the block application. Also, air-based block reinforcement with recycled waste carton pulp provide low environmental footprint and of consumption and good comfort inside the building due to the certified balance between strength, density, water absorption, and ductility. Also, by using this cellular fiber, you can improve the crack resistance and the weight resistance against external factor in our air-based material. It requires to use one cycle of wetting and dry treatment will help to have a good dimensional stabilization and reduce the moisture absorption capacity of our material. We recommend also to use accelerated carbonation process will help us to reduce the pH of the material, who can help to raise the durability of the cellular fiber with the time. So what is the contribution to knowledge? The suitability of agricultural crop residual biomass and municipal waste as a raw material to achieve a satisfied balance between thermal comfort, mechanical performance, and durability of building block. The study showed that the recycled waste carbon fiber are green sustainable material which can be used to improve the strength, toughness, reduction of crack, crack of shrinkage. This study also has used material science approach to evaluate the possibility replacement of bleaching fiber by recycled fiber to promote resource conservation and circular economy in the building industry. Also, the mechanical, physical, thermal, and durability properties of this material suggests the suitable application of this cellulose fiber as a lively building in all countries where there is a pressing need of housing solution to solve both energy and environmental concerns. So that's the publication what has been done from this project. The acknowledgement, we acknowledge the Minister of Secondary Education and the Department of Mechanical Engineering and Set of Douala. I would like to acknowledge the Pan-African Material Institute, African University of Science and Technology, African Development Bank for the financial support for this study. My humble thanks go to the entire management of the African University of Science and Technology for the support according to me. My sincere appreciation to the Laboratory of Construction and Rural on the Faculty of Animal Science and Food Engineering of University of Sao Paulo, Brazil, for their two fellowship that I did there. I would like also to thank Professor Omalo, Professor Wale, Professor Junior, Dr. Ronaldo, Dr. Miso, Dr. Mazi, Dr. Bello, Dr. Vitalis, Madam Odef for the helpful technical discussion during my study. Special thanks to my supervisor for their great support, guidance, and monitoring. All the members of the material science and engineering on my research friend, also my family, my wife, my child, my mother, my brother, my sister, and all my friends. Thank you for listening.
Thank you, Mr. Tido. If you want to sit down, please your water.
Yes, thank you.
You want to take water, you want to sit down for a day. You are a young man, so you can.
I understand.
Okay, thank you for that presentation. Now we are ready to go through the questions and discussions. As I said earlier, we're going to start with the external examiner, that's Professor Tonoli. I have requested all the examiners to send in a report. That report will include any corrections you want on the thesis, all those minor things like grammatical errors and all those other ones. You should articulate them in your report. You can even annotate the thesis wherever you want correction to be done. If you haven't done that, please do so and send to me. If you make corrections within the thesis, that will be fine. I will send it to the student for him to improve on the thesis. The requirement of African University of Science and Technology is that the candidate must take at least 4 advanced courses in materials. This candidate has done that, and the candidate must obtain a minimum of a B on the average, or rather a minimum of a B in each of the courses. This candidate has done 10 courses. He actually did 10 courses, so he did an overkill of our PhD courses. The other requirement is that the candidate must have taken the qualifying exam. This candidate has also taken that qualifying exam and passed. The final requirement is that the candidate must publish at least 2 papers in Scopus Index journals. And these 2 papers, the candidate must be the first author. This candidate has also done that, and I think I shared all these information on the exam. So, in terms of meeting the requirements, that has been done. But the work of this examination committee is to examine the student and be sure that he understands. He's actually the one that wrote the thesis and did the experiments or whatever. And if we are satisfied, we then recommend to the university to award the PhD to him. So that's what we want to do now. So we start with the external examiner. You will either make a comment or ask questions, and then we listen to the response from the candidates. At the end of it, you will let us know if you are satisfied or not. The same thing will apply to the others. So we'll be moving from one person to the other. After the external examiner, we move to the supervisors. Supervisors can still disagree. If they don't want this candidate to go, they will let us know. So we'll start with Professor Tonoli. You have the floor.
Okay, thank you very much. So it's an honor for me to participate. Thank you for inviting me. So I have some just brief questions. So congratulations for the work. So I think you did a large experimental part. So we can see that you did several experiments. You have used several characterization techniques. So I think you did a good work. So I would like to ask you some things. So the first one is about the difference of volume of the fibers. So about the volume of these fibers instead of the weight. So do you believe the difference of volume between the fibers have some influence on the results? What do you think about that? Okay. When you compare fibers, different fibers, so what is the difference of volume of those fibers and how it can influence?
Well, thank you, Professor, for the question. The first part we did a dance, basically dance on the different fibers. We realized that by using recycled fiber, we were having a high density compared to the virgin fiber. And now during the test, we just evaluate the mass of the fiber during the test. We didn't evaluate the density, the volume of the material during the experiment. But you can calculate according to the density that we have, the mass that we have, you can calculate the volume, know what can be the impact of the volume for our material.
So what is the fiber that has more volume? Do you remember? Did you understand me?
Yes, I understand what you are saying. So, because the recycled fiber has a high density compared to the virgin fiber, if you take the same mass of the recycled and the virgin fibers, the volume of
You finish it?
no, yeah. If the volume of if the density of the recycled fiber is high compared to the one of virgin fiber, it means that the volume of the virgin will be high compared to the one of the recycled fiber in the batteries.
Okay.
Because we look at mass, the recycled fiber have a high density compared to the virgin. So it means that the volume of the virgin fiber is more consistent in the matrix compared to, is more high in the matrix compared to the recycled fibers.
Okay. And are you able to say what is the plant for this? What do you imagine about what are the species of plants for these recycled pulps? What do you believe? What is the tree? Maybe it's a tree. Yeah.
Yeah, the tree. We first because we know that almost 80% or 90% of the industrial pulping process is carved up. We just take in consideration that this fiber should be processing by carve process. But now the species, we don't really have more information about the species that we use to produce recycled fiber. But you can have an idea about the process that we have done. That's why during our discussion in the first manuscript, we justify, also in the second, we justify the high value, the high value of the mechanical property in using recycled fiber by the fact that we use a craft process for recycled fiber, who can have the impact of the mechanical property of that fiber compared to organosolved process. But the species of the plant we don't really have. So you can check. You can look at it.
Yeah, it's just a suggestion because when you did the literature review, so you can complete those informations with previous experiments about eucalyptus woods, pinus woods. They are the main woods used for carton paper. So when you did the literature review, you can maybe, I think you don't have time enough because you already published the papers, but you can discuss using information about eucalyptus and pinus that are the woods used for those carton papers.
Okay, thank you.
Yeah.
Yes, I'll add it.
Okay.
Okay.
You can still add it in the thesis.
Sorry? Sorry, I didn't understand. Sorry.
No, I'm saying that your suggestion can still be added inside the thesis, even though it's already published.
Okay, thank you. So sometimes I was confusing about the characterization of the fibers, because you did some treatments like bleaching, pulping. So sometimes in the results, for example, slide 14 in your presentation. So I believe you can explain more about those fibers, if are they the raw material or if they are bleached, those characterized fibers. I didn't understand if you characterize it before pulping or after that.
The fibers who has been used after the characterization on the first project, the fiber who has been used for the second project is you understand by using organosolved process. For the bamboo or the one of recycle, you just use water to defibrillate it.
Yeah, you can be clear putting if they are before bleaching, for example, you can put in parentheses before bleaching or after bleaching or after pulping, just to be clear for the readers.
Yes.
So also, I believe you can improve the graphs about the fibers, the fiber characterization. Let me see here. Just a minute. Oh no. In the project 2, slide 26. So here here you can put all the axes of these graphs. You can put in the same scale, you know. So
Yes,
here, it's confusing when you put different axes here to compare. So here I have a question about the toughness and the toughness of these composites. So why do you believe that toughness and specific deformation, the final specific deformation, why they are higher for dry samples? Because I was expecting the contrary. So could you explain this? Why you have the higher toughness for dry samples?
The toughness by evaluating, here we just for these two graphs we selected we just select from different, maybe by different formulation, just select one graph who has been plotted here. But by applying stress, we realize that for the dry sample, we were having a
because the behavior is the bamboo had the different behavior than the recycled pulp. So I'm just want to know if you know why the toughness was higher for dry samples of bamboo.
Compared to wet samples.
Do you understand?
Yes, I understand, Paul. So you are saying that you are expecting to have high specific energy for wet flexural strength compared to dry flexural strength, due to the fact that by the presence of water, we have a low friction between fiber and matrix compared to the dry condition. I think
Yeah. But why it's for recycled pulp the behavior was different? Why you believe for recycled the toughness are lower for dry? Why do you believe that?
I believe that the toughness is low for dry due to the fact that in the presence of fiber, there are reduction of the presence of water between fibers and in the transition zone between fiber and matrix. When there is a presence of fiber, you will reduce the bonding between fiber and matrix, and so you will increase the pull out on the fibers. So since that normally we're supposed to have a high flexural strength here in the recycle and the weight condition compared to dry condition. So that is
Okay.
yeah. Like that.
Yeah, okay. So the other question is about the thermal conductivity. So I just want to ask you if you can explain the principle of work of this equipment you have used for thermal conductivity.
Yes, the principle of the equipment that has been used for thermal conductivity, we have two plates. We have the hot plate down, and we have plate down and the plate up. Yes. When we produce our disc, sample, we use a silicon paste to increase the the addition between the transfer of the energy from the plate to the fiber or to the composite. So when we apply stress, we apply heat in one phase, we evaluate the transfer, the conductivity, the transfer of the heat from one plate to other. Because there's one plate who is hot, another who is cool. So deception. Who is cold when we apply the heat.
Okay. In here, you talk about the carbonation, yeah, the carbonation. So the reducing of the pH. Yeah? So we show it here that a long time the pH decrease. So here you put the samples in a sealed bag or something like that, or you leave at you left this in the environment. What you did here?
For the test, we use the methodology developed by Mahmoud and we consider that during the production of our composite, the same paste who has been used for the composite will be used for pH determination. So we will use 10% of the water that we will, yes, 10% of the consistence of our stirring. We mix it together, stir for around 30 minutes after we determine the pH. After the pH for the first day, we have to condition our solution in the same curing condition than the composite by cover. We cover it by using a aluminum papers. Aluminum fuel, we put it inside our curing chamber. After 1 day, we did the test. After 7 days, after 14, after 28 days, to see what can be the evolution of the pH with the time.
Okay. And why the drying cycle is important, and how it can be done in practice? What do you think about? What you can say about that? Why the wet dry cycle is important for you? This material.
The wet dry cycle. So because our soil material, sometimes when it exposes to the weather agent, their removal of the particle of the wall with the time due to the heavy hand and also some contact with the heavy hand. So that's why we decided to use a wetting and dry sprinkler by using a 12 cycle of wet and dry, who consists us to store the sample in the water for 5 hours, after drying for 42 hours in the oven in 70 degrees. And when you remove it, you have to brush it by using metallic brush. And after we measure the weight to see what is the percentage of removal the weight from the first to the 12 cycle. So it can help us to have an idea about the durability against those weather agents or our material.
Okay. And I didn't understand. Have you tested different percentages of cement?
Yes, both. We started by 5% of cement, 7.5 and 10% of cement. Before starting the composite, we produced those composites with 5, 7.5 and 10%. Then after that, we decided to cure and do curing temperature by using 24 degrees at 70% relative humidity and 60 degrees with 100% relative humidity. So after 7 days, we did a concretive strength of those cylindrical samples to evaluate the concretive strength, and also we evaluate the water absorption, the porosity, and the density. It's from there now that according to the result that we got, we selected 10% at the temperature of 60 degrees as our matrix. We will be used as a material, as a matrix for the fiber reinforcement.
So you use the same percentage of fibers, huh? The same contents. Then you use just 10%, okay? When you change the...
For the determination of the stabilization, optimized stabilization, we didn't use fiber. We were just using soil and stabilizer. By varying the proportion, we were not using fiber. When we decided to use, according to the result that we got, when we choose 10%, it's then at that moment that we use 10% as a matrix and vary the amount of fiber in the 10% of cement as a stabilizer.
Okay. So you in the conclusions, you suggested to use carbonation, yeah, accelerated carbonation.
Yes.
Is that true? Yeah. And do you believe? Sorry. Before
I left Brazil, we started the carbonization process of the air-based material reinforcing the cellulose fiber. We realized that by applying carbonation, by following the same process that has been developed in air-based material, in cement-based material reinforcing the cellulose fiber, after the carbonization process, there was no continuity of the iteration process of our material. So the mechanical property were going down, and also they are absorbing more water compared to the fiber without carbonation process. So we decided to stop the analysis at that moment. We wrote a proposal which can be used as a postdoc by seeing what can be the optimum carbonization process of the air-based material, because in the literature we are using more cement as with cellulose fiber as a reinforcement.
Yes, I was thinking about if you believe there is hydroxide, yeah, calcium hydroxide enough to carbonate with that 10%. Do you believe is there enough calcium hydroxide?
I don't believe that is enough, because due to the first experiment that we did in the lab, the result was not really satisfactory.
Satisfying, yeah, okay. Okay. I think it's enough for me. So thank you very much again for the invitation. And I hope the other colleagues can contribute also. Thank you very much.
Thank you, Professor Tonoli. I want to thank you especially for agreeing to be the external examiner. And I'm really impressed with with the short time you had. You were able to go through the thesis and ask these very useful questions.
Yeah, thank you very much.
We'll continue to collaborate with you. So we'll come back to you at the end of all the questions. We'll come back to you to ask you if you would like us to award this degree. So we'll now move to the supervisors. Now, the supervisors are internal examiners, and so they've been working with the students. And because of that, I will restrict them to just 2 questions. The rest of your questions, they will pass on to me so that I will make sure that the students answers them or corrects the thesis. So I will start with Professor Savastano, who is the major supervisor. And we'd like to thank for hosting our students all the time. We'll still send more students as we find money. Thank you, Prof. Please go on.
Thank you very much. Good morning again, everyone. Thank you so much for being here with us for this defense of the thesis of Tido. I have followed all the work that he has carried out in our lab. He's a very dedicated, energetic student and worker. So during all the time he was trying to overcome the difficulties and to bring new results. So this is very nice behavior for one student, especially for doctorate students. So this is a pleasure for us having students like Tido, like Endeso, and many others that would like to come in the future for working with us in collaboration with our group here in Brazil and other partners here in Brazil, like Professor Tonoli is another very nice infrastructure in Brazilian University. So just few comments, Tido. In reality, I think you have presented 3 different phases of your project. So they are all in a sequence of findings that you had in a very short time that you had during your doctorate, but you can explore even more each one of those 3 phases of your study. I believe that you have explored local resources available in your country and in your region in Africa. But I also believe that you can go much further, deeper in this characterization of those raw materials. So some raw materials are with better results than the others. This is normal. This is expected. That happens. But anyway, they showed nice potential for future studies. So because when we finalize the first phase of your study, we realized that those carton board fibers, they behave better, but maybe because the other fibers, the local fibers, the cassava or the other local umbrella fiber, they could be better maybe prepared. And referring to one of those questions from Professor Tonoli, I would suggest that in your slide, you could include the density of those fibers. So maybe you could then compare, like he asked you about the volume of fibers, the percentage, the volume percentage of the fibers in the composite could be compared if you have this information available. So you can better discuss this maybe in your third paper that we are going to prepare many other papers, I'm sure, because you have enough material. So I'm not sure, maybe it's in the slide, probably in your slide 14, maybe you could, referring to that question, you could include that maybe for the future. Then you can make a deeper discussion on that, because this can be important for discussing your results. But I'm sure you have this in your data, in your experimental data. Did you calculate to all those densities of those materials that you are working with?
Yes, Prof, I did the density. I calculated the density of all the material, the raw material, of the cellulose fiber. It's just that
Yes,
I'm not yet using.
Yes, as we can see, we have different composition of those materials regarding to lignin, cellulose, hemicellulose. This is different from one to another, and that can impact, and also the impurities. Also, let's say, not those constituents of the lignocellulose material itself, but that makes part of the vegetable mass. So this can, of course, influence the density of the material. So maybe for the future, you could refine or improve a little bit the procedures of pulping or cleaning of the pulp. After pulping, you have to clean the pulp. So to remove those extra components, undesirable, let's say, components. And this is not a new thing, because actually the pulping and paper industry, they know how to do this. But of course, you didn't have time for that. But this can bring new possibilities as reinforcing materials for those local fibers, local resources. And then you can demonstrate in the future that your local resources are perfectly useful for this kind of reinforcing application. So that's my point. I would like to valorize the local resources, but sometimes we don't have time and we don't have the correct tools, because this is a multidisciplinary work. So we are sometimes focusing the fiber, we are focusing the composite for some in civil construction. We are not so experts in the pulping production or in the pulping cleaning for improving the capacity of reinforcement of those pulps. So, and then we sometimes do not give the correct value to those resources just because we didn't have time or enough infrastructure to maximize the capacity of reinforcement of those materials. So I think in your discussion, you could also maybe include these considerations to make clear that this is an ongoing work, that you are not exhausting work. So you are open possibilities, maybe, hopefully, for future students or researchers to go ahead and improve the performance, of course, focusing this target of reinforcing elements. So you have to make clear that your fibers are there for reinforcing the material. So they were not planned, they were not designed to be a carton board as the fiber used. We just disintegrated the fiber and used that as reinforcing. But they were not originally planned or designed to be reinforcing elements in a earth-based material. They were planned or they were optimized to be a carton board, to be a packaging material. This is a different application, and we have to have this in mind, that we have to change the focus depending on what is our target.
Yes.
Yeah, and just one more consideration about the toughness of the material that Professor Tonoli also explored during his dialogue with you. We should keep in mind as well that those earth-based materials, they are not planned to be used in wet conditions. So earth-based construction, one of the basic principles of earth-based construction, they need to be in dry conditions to keep their properties. performance. So the soil, even using a stabilizer, as you have done in your work, the amount of cement or the amount of binder you are using is very low. Huh? It's a small amount. So maybe what you should explore in your discussion should be that we are stressing the material to see how it behaves in a situation like this, maybe in an emergential exposition of the material. But in reality, since the design of those constructions, what we have to make very clear is that those materials should be far away from water. they should be protected from water. I don't know if you have discussed this or not, maybe doing this in a deeper way to demonstrate that those materials, yes, they can be exposed to water accidentally. They have to be safe, or they cannot be destroyed because of the security or because of the health of people using the building, sanitary conditions as well. But anyway, they are not planned to be exposed to water because you are material to some conditions that they were not planned to that. And this is not just with earth-based materials. Many other materials that we use in construction, they are not thought or they are not designed to be exposed to water. That happens with many other materials. Wood, for example, or particle boards, for example. If you expose those materials directly to the water, of course, they will be destroyed in 2 cycles. But anyway, I think you should. I don't know if you have explored this during your experimental work or not. How can you emphasize this in your work? What's your opinion?
In the work, when I was doing mechanical characterization of the composite with the fibers, we did wet and dry condition because according to the literature, there are minimum value of the flexural strain who can be accepted in the wet condition. So that value has been defined by Maskell et al. The value was high, no less than I think 0.64 megapascal. So when we evaluate, we realize that our material was more far from that value. It can be accepted as a material in air-based building material. That was just the criteria to evaluate the possible application of our material in the air-based building material.
Yeah, I like to provoke this discussion because in early times, for example, in Brazil, before the ceramics came, the use of earth-based material was very high. Huh? 19th century, 18th century, the old buildings all based in earth materials. And those were marvelous buildings. And with time, we forgot how to build using earth. So this revalorization or refinding the old techniques. And sometimes it's a mistake, in my opinion, that we try to make those different techniques. They have to behave like ceramics. They have to behave like concrete. They have to behave like steel. No, or they are different. They are not better or worse. They are different. And we have to respect the limitations and use them correctly, because like in old times when they were used as the unique material, they just had those materials, the people working in construction and building made that perfectly, and they knew how to work correctly with those materials. So they have limitations. I'm not arguing that we should use earth everywhere, but anyway, when using earth, we have to be very aware of those limitations and those potentials of those materials. And just another comment, maybe in the future, if you are considering working with carbonation, maybe you could change the binder. Maybe you could consider other binders that could have a much easier or faster or more efficient carbonation. For example, you could use directly lime if you want to carbonate that. So maybe you could stabilize your earth-based materials using lime. I don't know. So maybe for the future, you could also consider, or other students or other researchers could consider using lime to see how the behavior of the earth-based materials in comparison to ordinary Portland cement, maybe. So you had those two papers already published. Congratulations. So maybe in the future you can publish other papers. I hope, especially regarding the durability of the material, because I think this is always a question mark about those materials. As I said, you could also further explore the durability of those materials in another publication. So are you considering that? Are you preparing something else for the future in terms of publications? Or
Yes, so now we have around 4 projects for publication. As the third one who has been submitted already in Arabian Journal of Beauty or Science and Engineering. And we have another one that we are doing nano indentation, grid indentation of the composite reinforcing with nano-fibrillated cellular from raffia fibers. And also we have another that we are using the hybrid fiber from cellulose fiber and nano-fibrillated cellular to combine both of them to see what can be the implication of those variation of the scale in the reinforcement efficiency of the air-based material. So we are still, it's ongoing, the process of the manuscript.
so thank you very much. I am happy already. I'm satisfied. Thank you so much.
Thank you, Prof. If you haven't submitted your comments, please I will appreciate your comments. The same thing applies to the grading sheet I sent to all the examiners. You should score the candidate and then send that. Thank you very much. We'll now move to the co-supervisor, who is Professor Josepha. After that, we'll be going to Professor Ebenezer. So let's take Professor Foba, please.
Right. Thank you, Prof. I'll start by joining my voice to Professor Olma's voice to thank everybody who has contributed in getting us to this day. It's really made us happy. We want to thank Professor Olma for the on-site and constant, consistent supervision and support. Tido would not have been able to make it out there in Brazil without the extra support that he gave. We want to thank him from within the team and let others know about that. I would also like to add my voice to him to say that Tido has been an exceptional student
if by using those amount of stabilizer, we can reach the requirement of the air-based block material. We realize that by using all 5, 7.5 and 10%, we are having more than 6% after 6 megapascal after 7 days of curing. So there was a satisfactory result by using just composite without fiber in the as a reinforcement. Later now, but when we use now a fiber as a reinforcement, we didn't investigate more on the compressive strength. We were more that because regularly our air-based material, we were having a high performance in compressive strength without fibers. We were trying to investigate more what can be the response to the flexural strength, because that is the real challenge of the air-based material as a building, or the air-based material for building application.
But I think that for the future, it's preferable to, if you want to use your material for building construction, it's preferable to do compression test. I propose to do it in the future.
Okay, thank you.
If possible also, if you can also the area of temperature on the mechanical property of your extruded brick after 24 days, I think that it will be also better. I propose to continue your work and also study the erosion of your extruded brick.
Okay.
Concerning the form, in some picture, it's difficult to make it. Don't use the color to differentiate picture, to differentiate the curve. In some figure, use a different legend to differentiate your curve, because when you make photocopy, there is a problem of
Okay. Thank you.
it's difficult to make difficult to make a distinction between the curve. You have done a good job, but how will you use your nanofiber? Have you understand? Have you understood? Mr. Tido? Hello, Mr. Tido? I think that there is a problem of communication.
The network is back from AUSC, Prof.
Hello?
Hello, Prof. The network has gone off from AUSC, so we need to give them some time.
It's AUSC challenge. We lost connection temporarily. Hello.
Hello.
Hello. Can you hear me?
Yes. Yes.
Okay. Yes, we lost connection temporarily. We are going to reconnect, but you can go ahead. The candidate can hear you.
Yes. I want only to ask to Mr. Tido for the future to see how he can use nanofiber, because it's possible to have an application of those nanofiber. I congratulate Mr. Tido for the job done, And I think that in Cameroon, you can develop those application for realized extruded brick. Thank you very much.
Thank you, Prof.
Okay, thank you, Prof. Let me also appreciate you again for agreeing to be part of this examination at short notice. We'll reach out to you again in future. Thank you.
You're welcome.
We'll move to the other examiners. Dr. Ojo. Dr. Mesojo.
Yes, Prof. Thank you very much, Prof.
Please, the remaining examiners, maximum 2 questions.
Okay, Prof. Thank you very much for this opportunity. I think I would join everyone as well to really commend Tido. Worked very closely throughout this. And despite the challenges with COVID, he worked very hard and was able to come up with this result within this time. I think I just have one comment. So my comment with respect to the durability of the composite. Yes, because he has showed how we can use these different cellulose fiber sources to produce robust composites for building construction. But like Professor Holmer said, before now, earth-based materials were more popular than the conventional materials that we have in use now. But the major issue was durability with respect to water absorption, how they performed in those severe cases. And that's why, in my opinion, the conventional materials were able to replace the earth-based materials. So the resurgence we're seeing now is with the fact that we can use these materials in a more sustainable way. But research is looking at how we can improve the performance of these materials to be able to compare with the conventional materials. So I think we still need to look at the durability, and the biggest indicator will be the water absorption. So, but from your results, you show that we still have relatively high water absorption with the cellulose fibers as reinforcement. Even with the hornification, we still have between 20 to 30% moisture absorption, which is not a very good indicator with respect to durability. So Tido, what can you comment on other alternatives we have that we can use to improve and sort of bring down the water absorption of the composites? Because I think this is something that is good. This is an area that we can focus on, such that we're able to bring these materials to be able to compete with the conventional construction materials, and at least because they are more sustainable. So Tido, the major comment is can you comment on other methods or techniques we can use to improve or bring down the moisture absorption of the earth-based composites reinforced with natural fibers?
I'm suggesting that we can use the unification of our cellulose fiber, because the unification training has been shown in the cement matrix that it can help to improve the dimensional stabilization of our material. We also can physically reduce the water absorption of our fibers. From that, it can help you to have a good adhesion between fiber and matrix. They also, by using unification treatment, they have ensured that they help to reduce the alkalinity and improve the resistance of fiber to get alkalinity nature, as our purpose have a high amount of pH to the stabilization of the cell. I do that by using that unification and the value to improve to reduce the water absorption, improve the water absorption, humidity, and also increase the density of our fiber and fossil-based material.
Okay. Dr. Meso?
Yes, Prof.
Are you done? Okay. Dr. Meso, 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 are you done? Okay
Yes, there's just one comment. Just that we struggled to hear him. I think he was not very close to the microphone, so we couldn't really pick what he was saying.
Okay, I was saying that by using a bonification treatment as a foresight bonification treatment of cellulose fiber before using as a reinforcement in this material can help us to improve the dimensional stabilization of the fiber and also reduce the water absorption capacity of our material. By doing that now, they can also improve the roughness of our fiber, which will help us to have good adhesion between fiber and matrix. By having that good adhesion, it will help us to have a good mechanical performance of our APIS material. Also, by doing that unification treatment, it will help us also to reduce the resistance, to improve the resistance against alkalinity medium. As alkalinity medium will help us to a fiber to resist against the vibration in the high alkalinity medium.
Okay, I think thank you. That's all for me, Prof.
Okay, thank you. Let me also thank you for participating. As I said, this is one of our recent graduates. We keep inviting.
Hello? Hello, Prof. We've lost you again.
It is just like.
Maybe NEPA took the light. You know our issues there.
Dr. Kigozi.
Kigozi, you can't be serious.
Dr. Ify, I'm serious. Even last time when I was presenting, when it came to midday, NEPA took the light, then brought the light back. So those are the challenges we have to solve.
Yeah, I believe hi, Moses. So when I was presenting mine.
Otherwise, how is everyone let's keep the platform moving until they connect back, because it's like all of them have gone off because they were using the line, but it's off.
Hello, hello.
Then by
Hello,
12.
sir.
Yes, sir.
Hello.
Yes, Prof. We can hear you now.
Okay, thank you. So thank you, Dr. Meso. Sorry, I think we have a little technical problem.
Okay.
So we are hearing all the things Moses was saying. So maybe we reconsider his PhD. Okay, so let's move to Dr. Obianyo. Dr. Ify, please, we'll listen to your comments and questions. Not more than 2.
Okay. Hello, Prof. Can you hear me?
Go ahead,
okay.
Yes.
All right. Thank you, Prof, for this great opportunity. I am so much grateful for this opportunity to participate in this defense. And I want to congratulate Tido for this great work. Indeed is a robust work. And without really taking our time, because we have less minutes for this defense, I want to quickly go to slide 12. Please, can you go to slide 12? I want to find out at what temperature do you actually did your fiber modification using the pulping process? At what temperature and pressure? And what informed those temperature and pressure that you use for your fiber pulping process?
Slide what? 12?
12. Yes. Oh,
it will be from slide 27.
Yeah.
It says slide what?
Go ahead, it's okay.
The first one was on slide 12.
Okay, go ahead.
Okay, and
Okay.
I'm asked at what temperature and pressure the Tido conducts his pulping process for the fiber modification. Then the second question is from slide 27. And I want to also join others to comment on this thermal conductivity. We found out that looking at the results of the thermal conductivity, we found that the more as we increase the fiber content, the fiber conductivity kept decreasing. But something happened after 7.5 with recycled fiber, carton pulp fiber. We found out that after 7.5, instead of the thermal conductivity to keep decreasing, it shot up and it increased. So I want to know the mechanism. I want to know if Tido were able to find out the mechanism behind the sudden increase after increasing while the fiber content is being increased. What prompted the metrics to indicate that the thermal conductivity started increasing after 7.5% fiber content? Thank you.
Okay, thank you, Dr. Ifi, for the question. So the first question was about the temperature application that we use for the popping process. From if you are taking one process as a organosoft popping process, we are using the temperature of 190 degrees inside the reactor. By using 120 degree and 90 degree in the reactor, to start on the beginning, we set the reactor to achieve 120 degree for 2 hours. So the temperature, more the temperature it keep going, more the pressure in the reactor will completely close. The pressure also are increasing. But when we reach our temperature of 120 degrees, the pressure in the reactor was around something of 150 megapascal, the pressure in the reactor. So we can just take the reactor gave out the pressure around 150 megapascal in that organosoft popping process. So now, according to the question of the water, the thermal conductivity, more we are increasing our fiber in the matrix, there are reduction of the thermal conductivity, which is constant with the literature. But the problem that we realized that by using more than 7.5 at that level, we were increasing the
It seems we've lost you. Are you there, Tido?
I think we've lost them again.
Yeah, it seems so.
So you just have to be patient. Hi, Ify.
Yeah. Hi. White cloud. How is everything going on?
Very well, thank you. And you?
Thank you. Okay. We are still waiting for AUSC to connect.
Please, I need the answer to that part, that question you asked. I'm sure you didn't get the last part. I need to get the answer to that last part.
Okay, is it about the thermal conductivity or about the
sudden shoot, the sudden increase in the temperature?
Yes, what's the mechanism behind it? Because there has to be a mechanism. You can see the trend.
Yeah.
If you are looking at, if you have this, if you're looking at the graph, you see that it kept coming down at 5%, at 7.5%, also kept coming down. But immediately after 5%, we discovered that it's recycled carton pulp composite.
Let me see. Hello? Hello?
Ify. Oh.
Hello, Dr. Ify.
Hello.
Can you hear us?
Yes, sir, we are hearing you now.
Okay. Yeah, it seems as if the microphone of this computer.
Hello?
No, yes, we can hear you, Dr. Vitalis.
Right.
Hello? Hello, Dr. Ifi?
I think if he has
Hello.
gone up now.
Yes,
Hello?
I'm understand you. I'm hearing you. Hello. I want to be sure you are hearing me.
Yes.
Okay. Thank you to invite me to attend this defense. I want to congratulate the Mr. Tido for his work. I have just one question. I want to know if this study is close to be applied for industrial issue, and if he can give us how many times this application can be realized. Thank you.
Okay, thank you, Dr. Aisi, for the question. This fiber has been done in the lab just for a lab scale, but now we can also apply it to the industrial scale by using cellulose fiber. And that is why during the process we produced many samples. It was representative or when we were doing the flexural strength, there was minimum of 6 samples who has been done, so to evaluate the statistical impact of those results. So I think that this work can be also applied in the industrial scale using the same formulation and the same pressure of the extruder, the same speed of the extruder.
Thank you.
Okay, thank you, Dr. Aisi, for participating in this examination. We've taken all the examiners online. I will now give opportunity for the faculty that are here with me, but I will reduce the number of questions to 1. If they have more than 1 question, they can write and send to me. So I will start with Dr. Shola Odusayan.
Thank you, Tido, for presenting a very good work. I saw that you use extrusion to disperse your fibers, and I would have loved to see the discussions on the most important dispersion parameter. Is it rotor speed? Is it time? Is it the length to diameter ratio of your die that will determine the dispersion? And also, I would have loved that you show that the fibers were well dispersed within the matrix. That could be future work. But the key thing I want to ask you is about the aspect ratio of your fibers. How did you unify that, and what impact did that have on your material?
Yes. Okay, thank you, Dr. Shola, for the question. So the aspect ratio has been evaluated because on the beginning we were having 5 species of fibers. Now, after producing the cellulose fiber, we evaluate the aspect ratio, the morphology and the aspect ratio of each type of fiber. It's based on that we realized that we were having around almost 50, the value of the aspect ratio from the bamboo fiber and the recycled fiber. So it was high compared to the value that we got in the raffia and cassava bag, was around some value of 12, 20. So that is some criteria we help us to select those 2 types of fiber for the production of the material. But now the virgin fiber were having high aspect ratio compared to the recycled fiber. We're expecting to have a high reinforcement efficiency for virgin fiber because more you have a high aspect ratio, they are also increasing of the dissipation energy, dispersion friction energy during the pull-out of the fiber. But we saw that the result was different. So we showed that the recycled fiber, due to the fact that by producing recycle is behave like this unification treatment was the appeal can have an impact in the roughness that got more impact compared to the aspect ratio of the fiber, because we're expecting to have a good reinforcement efficiency by using virgin fiber compared to recycled fiber due to the high aspect ratio, but the result was not consistent, was not coherent to those values.
Okay, thank you, Dr. Shola. We move to Dr. Bello.
Thank you for the very good presentation. The Prof has restricted us, but I'll still ask, why do you refer to bamboo as a non-wood fiber?
Yes, I use bamboo as a non-wood fiber because when you by classification, bamboo is considered as a grass fiber. Grass is not considered as a wood. Grass, like those grass. Okay, grass. Yes, classification in the agri engineering that consider bamboo as a grass is not a wood. It's not a wood.
And the last one is, when you did your poll, you use sodium hydroxide.
Yes.
What about if I use potassium hydroxide? Is it going to be any significant difference?
I use sodium hydroxide because in the literature we are more work has been done on using sodium hydroxide. According to potassium hydroxide, I'm not yet, because when we are using soda hydroxide, it defined as the soda pumping. It's already have a methodology of it in the literature. But by using potassium hydroxide, I've not yet saw in the literature, but we can do it for the future to see what can be the impact of those fibers.
Okay, thank you. Like I said, if you have more comments, please articulate it and send to me so that we can use it to improve the thesis. The last but not the least is Dr. Vitalis.
Okay, thank you very much, Tido, for this great piece of work. I have a couple of questions, but just one that I'll ask. So, with regards to the reinforcement, you said that the reinforcement, as a result of it, there's a transition from brittleness of the composite to pseudo-ductility.
Yes.
And Professor Beneza raised something that it's good that you study the influence of temperature on the physical mechanical properties of this composite. So at what point do you think will this transition occur? For instance, there may be thermal cycling and other environmental conditions that these bricks or blocks will be exposed to. So at what point will this transition happen? Because why I'm asking this is because if you remember the famous Titanic ship, you must have watched that movie.
Yeah, yes.
You know, it failed. That failure was a materials problem. So there was a transition from ductility to brittleness of the steel that was used to make some of the components. And it was because of the sulfur content that was high. So at what point will this transition that you're talking about in this project?
Due to the temperature? Or...
It can be due to temperature, it can be due to other environmental conditions, it can be due to even the composition. So did you bother about that?
The behavior, we said that our fiber, there was transition from pure brittle to ductile material due to the fact that there was the curve was showing a strain hardness behavior because they were increasing of the stress after the first crack present in the fiber, in the composite due to the crack arresting. So now the impact of the temperature, because we realized that by using the sample who has been weighed in the water for 24 hours before testing, and the one who has been dry at 60 degrees for 24 hours before testing represented the same behavior. So maybe by increasing the temperature, can have an impact, because it has been shown that by analyzing the thermal degradation of the fibers, by having a temperature of almost 100 degrees, there are some degradation will appear on the structure of the fiber, who can have a significant impact on the degradation of the fiber in the matrix. That can have also an impact on the mechanical and also on the mode of rupture of our material. I think that it can be a future work to study the improvement of the temperature to see what can be the impact. So it will depend also on the application of our material, because now our material is applied for the urban houses. So we know that the temperature range maximum, it can reach the 40 degrees. So we are just characterized according to the application of our material. If they can be a potential use of those material in maybe in the furnace or in this thing, we can now vary the temperature to know if it can withstand those temperature and during the loading.
Okay, thank you very much. I think we are getting to the end of this examination. I would have asked each of the examiners to indicate whether the degree should be awarded or not. But I think, having listened to all of you, it looks like everybody is saying the degree should be awarded, but there should be some modifications to the thesis. So I will request that each examiner will articulate what modification you want and then send them to me, so that I can get the student to do all that. And then, so with the question I want to ask, I'll reverse the question and say, is there anybody who doesn't want this degree to be awarded as at this point? If not, if not, I will invite, I think it's by consensus. If you have any objection, please write to me. Otherwise, because of time, we have just 10 minutes to round up because of power. I will request the major supervisor, Professor Homer, to make a pronouncement. And if the pronouncement is positive, then he should also congratulate the candidate. Professor Homer, please.
Yes, please. Thank you so much. I'm very glad to indicate Tido for this title of doctor, based on the response during this defense, and also based on all the work he has carried out during the period he was here, and also that I followed during his stay in Abuja. So I'm very happy to recommend and to support the granting the title of a Doctor of Philosophy to Tido, based on that performance.
Thank you.
Congratulations.
Congratulations. I would like to thank the external examiner, Professor Tonoli. I don't know if he's still online, for the excellent work he has done. Let me also thank the supervisors, Professor Homer and Professor Foba, and all the examiners that I invited at less than 2 weeks' notice, and they were able to attend. Would like to appreciate all of you, and want to thank you on behalf of the university for always working with us. Tido has been a very good student, not just being a student for himself, but also even assisting all the other students, those doing PhD and those doing masters. That is the essence of collaboration. You learn from others and you teach others. So we'll come to the close of this examination. Let me seize this opportunity to thank all our PhD students. I think we've had it very good this year. Last month, we had a defense like this. Oh, was it this month, Dr. Moses?
Yeah.
Today we are doing another one, and I believe, God willing, by early March, we will still have another defense.
Wow.
So we want to ask the other students to work hard to make sure that their papers come out so that we have more students graduating. Thank you, everybody, and congratulations to Dr. Tido.
Thank you.
Bye, Moses.
Congratulations, Dr. Tido Tiwas, Chancellors.
Thank you very much for everyone. Thank you very much. Thank you very much.
Congratulations, Dr. Tido.
Congratulations here.
Thank you.
Thank you.
Congratulations, Tido.
Congratulations to the supervisor.
Thank you very much.
Congratulations, everybody.
Tido, Dr. Tido.
Congratulations.
Yeah, yes. The pictures.
Well done.
Picture, yes.
Komaja, I can see you.
Tido.